So welcome again in this lecture. Let us continue with uniform continuity. So today we'll learn how a uniformly continuous function defined on a non-empty subset of R can be extended to the whole of R. So the result is, let A be a dense subset of R and let F from A to R be uniformly continuous then there exists a unique uniformly continuous function G from R to R such that f of A is equal to G of A for all A in A. Okay? Okay. So let us prove. So here our job is to define a uniformly continuous function from R to R such that this should be an extension of your original function f. That means f is the restriction of G. Okay, so let us start. Proof. What is given to us? We are given that A is dense. So since the closure of A is R, therefore for each real number x, there exists a sequence an in A such that an converges to x. Okay. Since f is uniformly continuous, uniformly continuous function takes a Cauchy sequence to a Cauchy sequence. Okay. Since f is uniformly continuous, f of an is a Cauchy sequence in R, and definitely every Cauchy sequence in R converges. So this converges. In fact, continuity will do converges in R. So that means for each real number x, I have a sequence an in A such that the sequence f of an converges in R. Okay? Okay. Now, I want to define, we define G from R to R by G of x is equal to limit of the sequence f of an. This is how we define G. But the question is the function G well defined? That is a question. Why this question arises? The reason is, we know that if you choose any x in R, there exists a sequence an in A, but there is no guarantee that this sequence is unique. There may be more than one sequence. There may be infinitely many sequences in A which will converge to X. But in that case, is it guaranteed that limit of f image of all such sequences will be same? Do you follow me? My question is, let an and bn be sequences in A such that both these sequences converge to the same limit x. The question is, can we say f of an and f of bn will converge to the same limit? Let us see. Let epsilon greater than 0. Therefore, there exists a natural number n0 such that mod an minus x is strictly less than epsilon by 2 for all n bigger than equal to n0, and mod bn minus x is less than epsilon by 2 for all n bigger than equal to n0. The important thing is, here I could have taken two natural numbers, say n0 and n0 prime, such that modulus of an minus x is less than epsilon by 2 when n is bigger than equal to n0, and modulus of bn minus x less than epsilon by 2 when n is bigger than equal to n0 prime. But if it is so then I can take the maximum of n0 and n0 prime. And whenever n will be bigger than the maximum of these two, both these two inequalities will be satisfied, modulus of an minus x less than epsilon by 2 and modulus of bn minus x less than epsilon by 2. So such tricks are now known to you because we have adopted this type of tricks previously also. So I have not written that line. Now it is quite obvious that how things are being done. Okay, so that's fine. So from here, what can I say? Therefore, for all n greater than equal to n0, what happened to the sequence an minus bn? I can say this is less than equal to mod an minus x plus mod bn minus x by triangle inequality. But we know that this is less than epsilon by 2 and this is also less than epsilon by 2. So their sum is less than epsilon. Okay. So what does it mean? For every epsilon, there is a natural number n0 such that modulus of an minus bn is less than epsilon. So it means, therefore, some problem. Therefore, yeah, sorry for the interruption. Therefore, mod an minus bn actually converges to 0. But f is uniformly continuous. This will imply since f is uniformly continuous, this implies mod f of an minus f of bn converges to 0. And this implies limit n goes to infinity, f of an is equal to limit n goes to infinity, f of bn. So the function g, as we have defined, is actually well defined. Why? See, this is how we have defined g. So whatever sequence you choose, whether it is an or bn, it doesn't matter. There may be infinitely many sequences an for which an converges to x. I will take any one of them and its limit will be same as the limit of the other one. So gx is unique in R, right? So therefore, it actually guarantees, therefore G is well defined. Okay. Okay. So I have to prove that G is uniformly continuous, G is unique, and the restriction of G to A is F. Okay. Okay. So let us first of all show that if X is in A, then Gx and Fx are same. So let say A belong to A. Then the constant sequence A dot dot dot, this converges to this converges to A, and therefore what happened to G of A? This is equal to, by definition, limit n goes to infinity, f of the sequence an, here an is A, so limit has nothing to do, the limit is also f of A, so it is simply f of A. So I'm done. It proves that f is the restriction of G to A. Okay. Now let us prove that G is uniformly continuous. How to do that? Let epsilon, already I have taken epsilon once, no matter, but still let epsilon prime greater than 0. Anyway, if you don't want to choose, already epsilon is chosen. So let me not write anything, epsilon is already there. So I can say that by uniform continuity of f, there exists delta greater than 0 such that mod fa minus fb less than epsilon for all ab in A with mod A minus B less than delta. Okay. Let me choose X and Y from R. Let XY belong to R with mod X minus Y less than delta by 2. Okay. Since X and Y are real numbers, corresponding to each of them, there exists a sequence, say An and Bn in A, such that An converges to X and Bn converges to Y. Therefore, there exist sequences An and Bn in A such that An converges to X, Bn converges to Y. Okay? Fine. So what happened? Use the definition of convergence of sequence. Therefore, there exists a natural number n such that An minus X is less than delta by 4, Bn minus Y is also less than delta by 4 for all n greater than equal to capital N. And why I have got this capital N, you know it. Actually, there exists, say, N1 and N2, and then let us take the maximum of N1 and N2. or let us take any natural number which is greater than equal to both, then I am done. Okay. So therefore, mod an minus bn by triangle inequality less than equal to an minus x plus bn minus x less than delta by 4 plus delta by 4 is equal to delta by 2 for all n greater than equal to n. Okay. Now, consequently, you see, we have said that if A and B are in A such that modulus of A minus B is less than delta, then modulus of f of A minus f of B is less than epsilon. So here your An and Bn all are in A such that modulus of An minus Bn is less than delta by 2, obviously less than delta, for all n bigger than equal to n. So consequently, we can say what happened? Mod f of an minus f of bn, this is less than epsilon for all n greater than equal to n, right? This implies limit n goes to infinity mod f of an minus f of bn, this is less than equal to epsilon, right? But this implies, now modulus is a continuous function, so this is nothing but modulus of limit n goes to infinity f of an minus limit n goes to infinity f of bn, this is less than equal to epsilon. But what is limit n goes to infinity f of n? This is nothing but g of x minus g of y, and this is less than equal to epsilon. Am I done? Yes, I am done. But you can say that less than equal to epsilon y. So to avoid that, I can do something. Here, instead of writing epsilon, I can write less than epsilon by 2. Then automatically here it will be epsilon by 2. This will be less than equal to epsilon by 2, less than equal to epsilon by 2, less than equal to epsilon by 2, which is strictly less than epsilon. So I am done. If x and y are two real numbers such that modulus of x minus y is less than delta, then modulus of gx minus gy is less than epsilon. So g is uniformly continuous. Okay. What next? I am not done. I have to show that this g is unique, if possible. Now, question, can we say that the way I have defined g, I have defined g as limit of a convergent sequence f of an, and we know that limit of a convergent sequence is unique, so I cannot define g in other way, so it is unique. Is it the argument? Answer is no. Why? Because the way I have defined g, somebody may try to define g in some other way also. Who knows? I have not omitted that possibility. I have not proved that there is no other possibility of defining g. So now I have to show that if somebody defines some other function h, which is also uniformly continuous extension of f, then that h must be equal to g. That is to be proved. So let h from R to R be a uniformly continuous function such that the restriction of h to a is equal to f. That means h of a equal to f of a for all a in A. So I have to prove that g is equal to h. How to show that two functions are same? If two functions agree on each point of the domain, then they are said to be equal. So let x belong to R. Therefore, there exists a sequence an in A such that an converges to x. Now, what is g of x? By definition, g of x is limit n tends to infinity f of an. But as long as a is in capital A, f of a is same as h of a. So this is same as limit n tends to infinity h of an, right? But h is uniformly continuous, so it is continuous. If an converges to x, h of an must converge to h of x. So this is equal to h of x. And this proves this is true. The reason is since h is continuous. H is a function from R to R and continuous. This is continuous. So therefore, G equal to H, hence proved. So my G is unique. Okay, so this is the proof of the result. Okay, let us have some remarks after this. So remarks. Number one, if f from open interval AB to R is continuous, then it need not be bounded. Okay. It need not be bounded. For example, if I define f from open interval 0, 1 to R by f of x is equal to 1 upon x for all x in open interval 0, 1, then it is continuous but not bounded. But if a function is uniformly continuous from an open interval, if f from AB to R is uniformly continuous, then it must be bounded. Why? The reason is, you see, I'll use the previous result. The reason is, I can define a uniformly continuous function g from closed interval AB to R, such that the restriction of G to open interval AB is equal to F. This is uniformly continuous because the closure of open interval AB in R is closed interval AB. So this is uniformly okay. Right? Now this is uniformly continuous, so continuous, and a continuous function defined from a closed and bounded interval, that is from a compact set, is always bounded. This result is known to us. So G is bounded, and if G is bounded, then F is bounded. So this is uniformly continuous. So G is bounded, and this implies its restriction F is also bounded. So although a continuous function need not be bounded from defined from an open interval, a uniformly continuous function is always bounded. Okay. Second thing, and one important thing, in the result, although we have extended F, which is defined from some subset A to R, to a function G uniformly continuous from R to R. We have used the fact that A is dense in R, that is A closure equal to R. So actually we are extending F defined from the closure of A. Actually we have defined G from the closure of A to R. So that means any uniformly continuous function defined on a non-empty subset of R can be extended to its closure uniquely. And this is the result I have used here. Since the closure of open interval AB is closed interval AB, any uniformly continuous function defined on open interval AB can be extended uniquely to closed interval AB. Okay. Okay. I want to make another remark here. That is, if F from open interval AB to R is uniformly continuous, then there exists a uniformly continuous function G from closed interval AB to R. Okay. Such that f of x equal to g of x, or all x in open interval AB. If this is the case, then what is g of A? G of A is limit, G is uniformly continuous, so it is continuous, so limit exists. So that means limit x goes to a plus, that is right hand limit of the function g at a is g of a, because g of g is continuous, right? But this all x are in the open interval ab, because a is excluded. So gx and fx are same. So this is same as limit x tends to a plus f of x. And similarly, I can define g of b as limit x tends to b minus the left hand limit of g, and that will also be same as limit x goes to b minus f of x, correct? Okay, so these two limits, both these two limits actually, sorry, both these two limits exist in R. So if f is uniformly continuous from open interval ab to R, the right hand limit at a and the left hand limit at b both exist in R of the function f. So this is a way by which we can check whether a function is uniformly continuous on an open interval. For example, if somebody says, this is an example, if somebody asks you that what happened to this, f is defined from open interval 0, 1 to R, and f of x equal to sine x, okay, so sine 1 by x for all x in open interval 0, 1. This is continuous, everybody knows, but is it uniformly continuous? If this function is uniformly continuous, then the right hand limit at 0 and the left hand limit at 1 both should exist. But what happened to limit x tends to 0 plus sine 1 by x? Does it exist? Answer is no. This limit does not exist, right? So this is an exercise for you to check that this limit does not exist. This is very easy to check. If you know the definition of limit, you can easily check. The hint is you take any two sequences, xn and yn, both converge to 0, and with positive values, both converge to 0, and none of the terms equal to 0, but f of xn and f of yn, they converge to different limit, or one of them doesn't converge at all, right? Okay, this does not exist. So since one of the limits does not exist, it means the function f is not uniformly continuous. Okay? Okay. But now my question is, okay, fine, I know that if f is uniformly continuous on open interval ab, then both these limits, left hand limit at 1 at b and right hand limit at a, both these two limits exist. Is the converse true? If f is a uniformly means if f is a continuous function from open interval ab to R, such that both the limits, the left hand limit at b and the right hand limit at a exist, can we say f to be uniformly continuous? The answer is yes, that can also be said. So now let us prove this. So result, let f from open interval AB to R be continuous and limit x goes to a plus fx and limit x goes to b minus fx exist in R, then f is uniformly continuous. So now we are happy. This is both necessary and sufficient condition. Proof. Okay. So we define G from closed interval AB to R by G of x is equal to limit x tends to a plus fx if x equal to a, f of x if a strictly less than x, strictly less than b, and limit x tends to b minus fx if x equal to b. Right? Okay, I have defined it. Can we say G is continuous? See, only we have to check the continuity of G at A and B, because other than A and B, G is equal to F and F is given to be continuous, so G is continuous. So only we have to check at A and B. How to check? If I can prove that the right hand limit and left hand limit both exist and the common limit, of course, not left hand limit, one. Okay, so sorry for the inconvenience. Due to some technical reasons, actually, I got disconnected. Okay, so I have to check whether G is continuous or not. And for that, I have to check continuity at A and B. That you have understood. So, we have G of x limit x tends to a plus is same as limit x tends to a plus f of x. Because you know the definition of limit, here the x we are taking, these are inside the open interval AB. And by definition, this is my G of A. And limit x tends to b minus G of x, this will be same as limit x tends to b minus f of x, and by definition that is my G of b. So since the limiting value is equal to the actual value, therefore G is continuous at A and B. Again, gx is equal to fx for all x in open interval AB, and f is continuous on open interval AB. So G is also continuous. Therefore, G is continuous on open interval AB and hence on closed interval AB, because two endpoints have already been checked. But every continuous function defined from a compact set is uniformly continuous. Therefore, G is uniformly continuous. So its restriction F has to be uniformly continuous. Hence, it follows that if the restriction of a uniformly continuous function is obviously uniformly continuous. So this is uniformly continuous. Clear? So let us see an example. For example, let us take the function f of x equal to x sine 1 upon x for all x in open interval 0, 1. Now, this function is continuous, we know. Is it uniformly continuous? Simply you have to check two limits. Limit x goes to 0 plus fx. This is the standard limit, you know it is 0. And limit x tends to 1 minus x sine 1 by x. What is this? This is sine 1. So sine is a continuous, this function is continuous. So continuous at 1. So that's fine, sine 1. Why continuous at 1? Reason is, you see, 1 by x is a continuous function at 1. So sine of this means composition of two, sine function is continuous, composition of two continuous function is continuous, then x is continuous, product of two continuous function is continuous. So both these two limits exists and f is continuous. So we can say f uniformly continuous. So this is the end of uniform continuity. So from the next lecture, we'll start monotone functions. So we'll start it from the forthcoming lectures. Okay, thank you.